Hello and welcome to Mathematics with Simon. I'm Simon. Today we're going to look at the properties of the modulus and argument of complex numbers. And in particular, we're going to prove two interesting, useful and beautiful properties. The first is that the modulus of a times b equals the modulus of a times the modulus of b. And the second is that the argument of a times b equals the argument of a plus the argument of b. So first thing is it not obvious that mod a times b equals mod a times mod b? Well, it is going to be obvious because we're going to prove it, but what I would say is this. Is it true that mod a plus b equals mod a plus mod b? It is not true. For instance, if we just take normal real numbers, or real numbers, mod of 7 plus minus 7 is not equal to mod 7 plus mod minus 7, because 7 plus minus 7 is just 0. So the mod of 0 is 0, and that is not equal to 7 plus 7, which is 14. In a similar way, if we just take a simple complex number, 1 plus I, mod of 1 plus I is not equal to mod 1 plus mod I. So it's not generally true, because mod of 1 plus I is root 2. It's 1 squared plus 1 squared, square rooted, and the mod of 1 is 1, and the mod of I is 1. In fact, what we can say is that the mod of a plus b is less than or equal to the mod of a plus the mod of b, and this is connected with the fact that the shortest distance between 2 points is a straight line. We'll come to that in a future video. But in the previous examples, 0 is less than or equal to 14, definitely true. Square root of 2 is less than or equal to 2, also true. So if we flick back, that's the 0 is less than or equal to 14 example. That's the root 2 less than or equal to 2 example. But it is true that mod a times b equals mod a times mod b. And we're going to prove it by grinding it out, which is often a very effective method. So we're going to use c plus di as a. We're going to use e plus fi as b. Times them together, we get ce minus df plus cf plus dei. Trust me, or do it yourself. I mean, I'm going to do this one, but I'm not going to do them all because it does, C times E is CE, DI times FI is DF, and then you get I times I is I squared minus 1. Okay, I'm going to do them all. C times FI, CFI, and then DE times I, DEI. Okay, so we've expanded it all out. Not that hard, is it? And then the modulus of this, we have to square both terms and then square root them. So we've got to square this, and square root them. So square of CE minus DF, C squared E squared minus 2CDEF, CE times DF, CDEF, there's two of them, plus D squared F squared. Then we've got to add on C squared F squared plus 2CDEF, timesing these two together, there's two terms, plus D squared E squared, the back bit. Then we notice that minus 2CDEF and plus 2CDEF definitely cancel. So we've got C squared E squared plus D squared F squared plus C squared F squared plus D squared E squared, which we can factorize as the square root of C squared plus D squared times E squared plus F squared. Then, by the rules of surds, we can change this into square root of C squared plus D squared times the square root of E squared plus F squared. Strictly speaking, to stay consistent, instead of putting a dot there, a dot is correct, but we should really put in a times sign. Look at that. It's all the same, right? And then C squared plus D squared is the mod of C plus DI. E squared plus F squared is the mod of E plus FI. So we have shown that the mod of the two numbers times together is equal to the mod of one times the mod of the other. Right, let's think about arguments. So if we have a point z, this is z up here, with modulus 1, its imaginary part is y, its real part is x. Sine theta equals opposite over the hypotenuse, so it's y over 1, which is y. Cos theta equals adjacent over hypotenuse, x over 1, so it's x. So you can write z actually as z equals cos theta plus I sine theta. We just put in cos theta for x and we put in sine theta for y. So z equals cos theta plus I sine theta, where theta is the argument. And actually, sometimes we write this as cis theta, and we think of cis as an operator that acts on theta to give us a complex number. So given any angle theta, we can apply the cis operator and get a complex number, in this case with magnitude 1. What about if z had modulus r? So not just 1, but r. So here, sine theta equals the opposite over the hypotenuse, y over r. Cos theta equals the adjacent over the hypotenuse, x over r. So we multiply both sides by r here. We get r sine theta equals y, r cos theta equals x. So we can put in r sine theta and r cos theta for y and x respectively. And we get z equals x plus iy. Z equals r cos theta plus I r sine theta. And we can factorize this as z equals r cis theta. So take the r's out. And this is r cis theta. So here's what we're going to do. We're going to take two complex numbers and we're going to express them in terms of their mod and their argument. So r cis theta times t cis phi. And we're going to expand these out. So we just take the r times the t, because these are all multiplied together, we can just rearrange the order. R times the t, then we've got cis theta times cis phi, and then we've got to multiply all the terms. So cos theta times cos phi, cos theta cos phi. I sine theta times I sine phi. I squared is minus 1, so it's minus sine theta sine phi. I cos theta times sine phi is that times that, and then I sine theta times cos phi is that times that. And then we notice that this thing on the left, cos theta cos phi minus sine theta sine phi, is just cos theta plus phi. And we notice this thing on the right, we can take out I and we get something in here, cos theta sine phi plus sine theta cos phi, that looks like sine theta plus phi by the sort of compound angle formulae for cos and sine, which you'll learn in trig. So this cos theta plus phi plus I sine theta plus phi is just cis theta plus phi. So what we've got is, we've got a complex number with modulus RT, and this backs up what we showed earlier, which is the modulus of the product is the product of the moduli, moduluses, however you want to pronounce it. And the argument of the product is the sum of the arguments of the things you're multiplying together, the complex numbers you're multiplying together. I hope you like this. Please hit like if you did. Please, you're very welcome to subscribe and hit the notification bell. I'd love to hear your ideas, things you'd like us to look at, and most of all, absolutely, I hope you enjoy your mathematics. Thanks for watching. Bye.